let's introduce a stochastic component into the data. Okay? So an additional stochastic, which is, W. We already have seen. Okay, so I already. By the way, I have an attitude. You probably understood. Okay? I do intentionally, but I don't explicitly say. So I believe that the knowledge, okay, is a long-term understanding, is a long-term process. Okay, so you need to digest a little bit. So my strategy to let you digest in a semester, which is especially in 3 months. Okay, so it's not very long time to digest. So my strategy is the following. I try to touch the same topic in multiple ways. So I touch this way, the other way, the other way. So you will see that at the end of the story, it seems that I'm still talking always about the same topic. Okay? I only enrich with new details every time I discuss. I believe that this one is shaping you better than discussing all the cases in a aseptic way, and then try to push you to learn by memory, which is something that I don't want. Now, so I refresh again. So x is equal to theta plus w. So let's assume the case, we are in this model. Now, let's assume that x is the signal and w is the noise. Okay? So it might happen, So I have, x is noisy data, if you like. Okay? So x has a stochastic component onto the data. Now we have two different ways, And by the way, x, w, and theta are statistically independent. Now we have two major categories. Okay? Category number one is that the signal is not random. Now this might be the case where we have a sinusoid. Now the sinusoid, is not random. It's deterministic. It depends on the phase, frequency, and amplitude. But when I know amplitude, phase, and frequency, then everything is deterministic. Okay? So in that case, the signal might be deterministic depending on other parameters that I'm not discussing now. But in this case, theta is deterministic. Now my goal is to get to the probability density function of x. Okay? Now, if theta is deterministic, which means is a number, okay? So what is the probability density function of x? The probability density function of x, which is this one, when theta is deterministic, is a number, okay? Is the probability density function of w shifted by theta. Now, let me give an example, very simple, because so that you get convinced about that. Assume that w, okay, is with the mean that is 1 and with a covariance that is sigma squared. I don't know, it can be whatever. Okay, I take scalar. Right? So let's consider that theta, and theta is deterministic. Okay, so w is Gaussian. By the way, what I'm saying here is general. It's not for Gaussian only. Okay, it's for any probability density function. But so, let's make it very easy with w as a Gaussian. So, what is x? Okay, x, is normal. In this case. What is the mean? Now, the mean is x equal to theta plus w. Now, if theta is deterministic, is a number, okay, so the mean of x is the theta plus the mean of w, okay, which is theta plus 1. And the variance is the variance of w only, okay. So that means that, if this is w, and my probability density function of w, which is shifted in 1, okay, the probability density function of x is shifted by 1 of theta, which means shifted, okay, by 1 of theta. That's it. Now, how can I write shifting by theta? Now, the way to write shifting by theta is that I need to write, this is PWW, okay? Now, PW means is a function that depends on W. And this W is the argument of the function. Now, how can I write here? So I need to write that the shape is the same as W. So it's the function of W, which is shifted on the right by theta. Now it depends on x, so it is x minus theta, because it's shifted by theta. It's the same shape shifted by theta. That's it. Now, it would not be so exceptional if rather than having the probability, which is scaring everybody, okay, if I write here, I write on the other side, I write as a signal. So imagine that I have a signal, okay, I have a signal of, let me write in a consistent way. So I have a certain signal, and this signal depends on W, okay? But now, since x is equal to theta plus W, now when I write s of x, okay, since I want to write the same function, this x is x minus theta, because it's the same function shifted by theta. This one becomes a delay in the signal, okay? So if this one, if SW is a triangle which is centered in whatever, mu W, okay? This triangle should be here shifted by theta. So it is mu W plus theta. How do they write it? It is the original one shifted by theta, delayed by theta. Okay, this is the meaning of the formula. So if it is deterministic, the probability density function of x is equal to the probability density function of W, the noise, shifted by the deterministic term, theta. Now, this part will be very important when we need to do the estimation problem. Because most of the problem, we need to calculate the probability density function of the data. So the probability density function of the data, which means the stochastic part of the data, is coincident with the stochastic part of the random term, which is the noise, shifted, okay, this is a technicality, shifted by theta. This is what the case of deterministic one. Now, this concept will be the basis of a deterministic estimation, which is, the so-called maximal likelihood estimation method. It's a basis for that. Is the trick that we will use for that. Okay. Now, let's consider a different case where theta is a random variable with a probability density function which is P2. Now, what can we say on that? Now, what does it mean, a random variable? Now, a random variable is a deterministic variable, make it random. Okay? So, can we write something similar in case theta is deterministic? So, can we fix a theta? Can we take one realization of theta? Can we take one value? Now, we know that theta is variable, but we take one value. Now, that value happens with a probability that is established by p theta. But I can freeze that value. So, Now let's revisit. Okay. So what is a PWX minus theta 0? Now PWX minus theta 0 is the probability density function of x when theta is fixed. So let's say in a statistical word. Now that one is the probability density function of x when theta is fixed. Okay? This is another way to say it. It's clear? Which, you know, it depends on the first one, which is the same. Except I put theta 0. If you like theta 0, then you know you can put theta 0. Okay? So, but that one is for the choice theta equal theta 0, which means, you know, is temporarily deterministic. Temporary. It's, you know, I fix just one value. But now, you know, my deterministic part should be released because, I mean, theta is not deterministic. It's theta 0 with a certain probability, theta 1 with a certain probability, theta 2 with a certain probability. So since my goal is to get the probability density function of x, this x is unconditional with theta. What does it mean, this word unconditional? Which means when I wrote like here, the second part, I say, I'll calculate P of W, x minus theta 0. That one is the probability, which is indicated there, of x, you know, when I fix theta equal to theta 0. But you know, this happens with the probability that is theta 0. So when I take the probability of theta 0, which means I have a set of categories. So if I fix that to theta 0, these phenomena, these experiments happens with the probability theta 0. If I make theta 1, that this experiment happens with the probability theta 1. Okay? Now let me sketch in a very, you know, very funny way. So this is kind of saying that I can imagine that, you know, I have theta 0, theta 1, theta 2, okay, different experiments. Huh? Now when I fix theta 0, you know, I have the experiment which is P, W, x minus theta 0. If I fix theta 1, then I have P, W, x minus theta 1, and so forth. P, W, x minus theta 2, and so forth. Okay? So now, you know, this one is the condition. So it's P, okay, which is x theta equal theta 2. This is one Px theta equal theta 1. Px theta equal theta 2. Okay? But now, you know, theta has a certain distribution. Okay? So that means that there is this probability that these experiments happen. There is this probability that these experiments happen, and so on. So, you know, you can read this plot this way. So what I'm describing here is the P of theta. Okay? So what I'm going to do is the following, you know, what I need to do, I need to sum all that with a corresponding value. Okay? And this is what is written in the previous part. Okay? So now, so this is I need to calculate, okay, I need to have PWX minus every theta times the corresponding probability associated with that theta in the theta, which means, you know, integrating that. I integrate for all of that. Okay? I integrate for those. Okay? So, which means, you know, it's a convolution, it's a multidimensional convolution, because, you know, that one is a multidimensional convolution, because it's that's the way I did. Okay? When I indicate n on the star, means it's n-dimensional convolution. Okay? So it's convolution in the n-dimensional space. Now this one, the second part, is important Because this one is the basis for variation estimation in Kalman filter. Variation tracking Kalman filter. Okay? So the first one, is for one set of specific problem. The second one is for one set of the specific problem. And so what you are going to do, every time you have a problem, you need to ask yourself, is it theta that we will see, theta will be our parameter to estimate. Is it my parameter deterministic or random? First question. If it is deterministic, then we use this trick, or we use this rule. Okay? If it is random, we use the second rule. And it's important that we ask ourselves if the problem we are handling is deterministic or random. It's crucial, we say. Now, is it clear? Simple, we are putting one brick after the other. Okay? If we want to create a big house, we need to start from the fundamentals. Okay? And all the bricks should be in the right place. Now, let's make I don't want to spend more than 10 minutes on this. Okay? You have the slide, you can read by yourself. Okay? But my philosophy. Any complex random, any complex number is real plus another number. Okay? So it's a way to put together two numbers. Now it might be convenient, not convenient, it doesn't matter. Okay? So for me, in this framework right now is just placed in this way. So let's consider the case where I have a complex value x, which is obtained as a sum of two random variables. One is the real part and the other is the imaginary part. We call it u and v. Okay? Now I have a set of properties. For instance, when I calculate the expectation of x, x technically it's hidden here, computing the expectation of u and v. And you remember the rule. If I need to compute the expectation with respect to u and v of u, v goes away because it integrates to 1. Okay? So the same story. This is equal to the expectation of u plus j times the expectation computed on v, which is the mean of u plus j times mean of v, which I indicate as mean, as mu, which is the mean. So the mean of the complex random variable is the mean of the real part plus the mean of the imaginary part. But I indicate in a compact way this way. Now, another property. If I calculate the expectation with respect to x of the absolute value square of the complex variable x, okay, this one is the mean with respect to u of u squared, the mean with respect to v of v squared. Now, this one is totally different from computing the expectation of x squared. Now, because x squared, it is, if I just put x squared, so x squared is u plus jv times u plus jv, right? Okay, which is different from computing the absolute value of x squared, which is specifically, is u plus jv, and then it is u minus jv. Okay, it's not the same. It cannot be the same. So anyway, so when I substitute, it comes out that the expectation is equal. The expectation is equal to something which is different from the expectation of the previous line. It is the variance. Now the variance for the complex random variable x, which is obtained by u and v, okay, is by definition. This is the definition. You hear? They are making experiments. It's a monster coming. Okay, so by the definition, okay? Then I apply the rule. So, which means, I apply the rule. It's x minus the mean star, which is a complex conjugate. Then I keep on going, and then, it comes out that there's a variance on u plus the variance on v, okay? Then I can calculate the covariance, which is still complex. And then I can calculate that the variance is the covariance for the same value. These are just, to start. Once again, if there are two u and v, might be statistically independent, then the joint probability on u and v is the product. And for Gaussian, independence and uncorrelation is the same. Now, if, let's go to the point. So, this is the case for uncorrelated and independent. Now, let's consider the more general case. So let's consider the case where, I want to, let me sketch here. Now, everything we said can be reframed as 2 by 1 vector. Now, if you reframe everything as a 2 by 1 vector, you don't make any mistake. So that means everything we said holds, except that you need to order real and imaginary in the proper way. Now, so this is x tilde. X tilde is u, real, and imaginary. It's one step on the top of the other. I can calculate the expectation, but it's a vector of 2. I can calculate the covariance, but it's a covariance of 2 numbers. Okay? Then I can write the probability density function, but it's a probability density function of 2 values, which means, this behavior, okay, is the same as we discussed here. If you take these 2 variables and you consider one is the real part and the other is the imaginary part, you are perfectly right. Analytically, you are perfectly right. So for this reason, any complex valued problem can be mapped back to a real problem where you put the real part and imaginary part, one on the top and the other on the bottom. This is what I'm going to show you here. Okay. So if I have a random variable and I can write it this way, where it's a mean and this is the covariance, then this is a random variable, which is a vector of n values, is a vector of n reals, and is a vector of n imaginary. But rather than writing it this way, I can stack it together, n real and imaginary. And this makes the total number of numbers 2n. I don't make any mistake on that. I'm simply, reusing what I did. So I can go back and reuse what I did, and it's the common way to do it. So if you have a complex set of, if you have a complex signals, or if you have a problem where you need to handle complex valued random variables, you can stack real and imaginary part one on the top of the other. You can use everything we do, and nothing changes. Okay, there is one convenient case, and by the way, so I'm not repeating everything, okay? I think we already said that, that complex numbers is not something that you measure. Complex number is a convenient representation, okay? Which is very common in telecom, for instance, where you represent the real imaginary part of the signals. Real imaginary part of the signals are representing the in phase and quadrature of the pass band signal. Now there is a very special case. So that means that I can organize all these vectors, I can calculate the covariance, blah, 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 blah. Okay, now, it might happen, and this is a lucky case, it might happen, that these covariances, so this one is CUU, which is the covariance for the real part, CVV, which is the covariance of the imaginary part, this is CUV, which is the covariance between the real part and the imaginary part. Now, if these matrices, which means if the property between real part and imaginary part are such that they are invariant with respect to a rotation of the axis between real and imaginary part, and you know the way to rotate the axis between real and imaginary is just a phase shift. So if you have a real number and you have a real imaginary, so you have x equal u plus j. Okay. Now if I take this as a random vector, this one is a complex random vector which contains real and imaginary part of the random vector. If I apply a rotation arbitrarily by an angle I don't know, see. Okay. Now this means that I'm taking the real and imaginary part and then arbitrarily rotating. Now, if the property of the random variable x, which is complex, is independent on the rotation, we say that the random variable x is invariant by rotation, which means it's circular. So, if in this case, it is a circular complex random variable. Okay? If a u and v is Gaussian, that this property is for circular complex Gaussian variable. In a multidimensional case, this property, which luckily is represented in most of the cases, this property is collapsed by this relationship, the circularity condition. Circularity condition implies that CUV is equal to CV transpose, which means the real part and imaginary part, they can swap each other in some way. They have some symmetry rules. Now, truly speaking, this property is what I often can see in most of the problems, except some special cases. Now, when you find these special cases where this property does not hold, the random signals are called improper. Okay, improper random signals. So, these improper random signals are not so common that we are totally skipping that. So, this means that we are assuming that circularity condition hold for all courses. Okay. Remember, so this means that we are assuming that the property here, holds for all courses. Now, what does really mean this property, from a practical point of view? Well, it means that every time we have a transpose operation, if it is complex, it is replaced by a Hermitian operator. So every time we do with a real vector transpose, it maps back to Hermitian in a complex set. So very pragmatically, we derive everything for real, but whenever we need to apply for complex, we apply the Hermitian to any operation. So like, I mean, we calculate the least square problem. You remember the least square? So the least square, okay, we said that we had to calculate ax equal b, okay, and we need to solve by least square. And what was our least square? X was a transpose a to the minus 1, a transpose b, okay? But this means that if we are considering the problem with the circularity condition, our solution for complex value means that A is a complex, X is complex, B is a complex, a set of complex numbers. Okay, so that means that, if the matrix A is complex, okay, that one is composed by columns, and the column is n-dimensional space. But since it's complex, in practice, it is two n-dimensional space, because it's n-dimensional for the part, n-dimensional for the imaginary part. Okay? So rather than passing that way, which is something that you can do by exercises, so rather than passing this way, you can, you can verify that this is fully equivalent to write for a complex one as A Hermitian A to the minus 1, A Hermitian B. This will be the solution. Okay? So rather than, this is the very convenient way. This is the so-called remission, transpose to remission rule. So everything we do with the transpose, we apply to the remission. If you want to verify that, I said you can verify. So if this one is complex, okay, then you rewrite for complex. So the complex is that I have A now and X equal B. You need to write for complexes. So you can stack all the X as X real, X imaginary, okay, equal B real, B imaginary, and then you need to rearrange the matrix A. Okay, so you have A real real, A real imaginary, A imaginary, A imaginary real, A imaginary. Okay. So you revise all that. That means that our problem that is n becomes 2n. You multiply, assemble all the pieces, okay, until you get that this property is true. And so you can look at the book in case, if you want to go deeper into this subject. Okay. Now we need to start. I need to introduce a new part for today. Okay. Tomorrow we do some exercises, and we do exercises on what I call the basics in the exam. Every exam contains a basic part. The basic part means something that we are supposed to know. Okay? So the basic part includes what we are doing right now. So tomorrow we do some basic exercises. And when doing exercises on the basic part, I refresh the Z transform. Okay? So I make a joint part. Refreshing the Z transform for those that for those that know the Z transform. I am revising the property for Z transform for those that have never seen. How many of you have never seen the Z transform in your life? Never seen? 1, 2, okay, 3, okay. We will, so you will be more, for you will be more stressful, for the other will be very, walking on, having a compass. Okay. So this was the subject for the last half an hour today. I want to enter into the chapter 6. Chapter 6 means, starting the estimation theory. So, I mean, right now what we have seen, you know, it's a basic for me. So it's something that more or less you are supposed to know. Perhaps, you know, it was not framed in this way. I'm just taking the pieces that you did in other fields. I'm putting together a common framework, and then now we start. So I would say now we start. This is where we are. So what is the estimation theory? Okay. In general, in statistics in processing, we have a set of data and access the data. And this data depends on a combination of parameters. And theta is the parameters. Now, usually, you know, we model statistically X. So we try to find a statistical model of X. So this is the major difference between, you know, our course and let me say other courses where the other courses that they try to establish the property or estimating data, but not accounting for the statistical properties. Probably because they have a lot of data, like a big data system. You know, when you have a big data, you know, you have a data itself. The data itself is telling you how good or bad. But if you have to work with a limited set of data, that's another story. You need to know what is the accuracy of your estimator. So what is the accuracy of data that you get? So if you have, you know, if you have a big amount of data, let me say a different attitude. That is, of course, big data is much more intuitive than this. Okay? Because with a big data, you know, we have a lot of data. So what you do this way, you know, imagine your data is very huge. I mean, thousands of megabytes of data, many samples. I mean, the number of samples that we measure is 10 to the power of 8. Okay, that's huge. So, and the number of data is huge. So if I have this huge amount of data, you know, what I can do is I can take this 10 to the power of 8, and then I can fragment into pieces. Okay? Then I can train on this. So I can use this one on train. Okay? And then I can use the second part on verification. I can verify with the second part. Okay? So, I mean, from the training, I try to get the data. And then on the second part, I see how good or bad is the data that I get. Okay? So it's a totally different approach. I mean, it's more or less similar to try and error, because I try a model, I get the data, I put this data into the data, and then I verify if, you know, if it is good or bad. Now, in our case, you know, this is if you like, the big data approach. Big data means you have a lot of data, then you can do this, and then you can increase the complexity of the model, you can change the complexity of data. I mean, this data, you know, can be as big as you like, and because you have 10 to the power 8. I don't know, this is 10 to the power of 6, and this is 10 to the power 2. Okay? And then, I mean, overall, you can make whatever you like. And so it's not 10 to the power 8 minus 10 to the power 2, 1,000. Okay, so if you strip 1,000 data from that, it's nothing. Okay, it's nothing. So we have a different approach. We don't have 10 to the power 8. We have 100. We have 200. We have 50. Why? Because, you know, in our case, the data has a cost. So we cannot measure a lot of data. Okay? So, I mean, just to show you an example, I mean, imagine that last year when I started this semester, okay, I started the semester by making an experiment. And some remembers, okay, the experiment. The experiment was very easy. Every student has a cell phone. So every student puts a cell phone on this table. This one. I don't remember if the room was this one, but you know, this table, okay? And so what I did was the following. So there are 10 cell phones, okay? So since there was, so I sketched the experiment, but you know, I mean, we did physically, huh? So we did really physically. So there are 10 cellular phones. Okay, perhaps, I mean, we do after, okay? But anyway, so there are cellular phones. So there's a table. This is the table. By the way, this table, not a table, this table, okay? In the table, I fix some position, okay? In every position in the table, we put a cellular phone of each student. Okay, every student puts his cellular phone. Okay, and then what we did is that every student was running a program, and the program was a program which was capturing the accelerometer. Okay, so what I get is that, you know, I'm measuring the acceleration, so the accelerometer, so the MEMS which is this side in the phone. What was the purpose of the project? You remember? Who was there? Some, okay. So the purpose was the following. I was hitting here. Hitting means hitting, okay? So when I was hitting here, I mean, I get the path which was a wave, which was traveling, okay? And then what's happening in the wave, you know, after a certain delay, the wave's hitting the first phone. Then after delay, hitting the second phone. After the third delay, hitting the third phone, okay? So measuring the distance and the relative delay, I can get what? Propagation speed. The propagation speed of the elastic wave into this table. Okay, that was the physical experiment, right? Okay, how many phones? 1, 2, 3, 4, 10. So we could allocate in this table 10 cellular phones because I don't know. I put mine, put one, blah blah. So I have 10 cellular phones. So 10 cellular phones. So n equal 10. This is 10 cellular phones. The number of data is limited. It's not 10 to the power 8 cellular phone, which is the case where you study, you know, the social media phenomenon. Okay, where you study, like Facebook is using those amount of data to study and classify the user, the political attitude, and so on. Here we have 10 samples. We are sampling the table in 10 points because every cellular phone costs $1,000, 1,000 euro, 500. That costs too much. So we are in this setting. We are in a setting where n is limited. 10, 50, 20, 500, 100, 1,000 maybe. Okay? But it's not 10 to the power 8, 10 to the power 6. Or if it is 10 to the power 6, you know, we cannot use all 10 to the power 6 in a common way. So just to classify. That means that we need to know something on our experiment. We need to know, for instance, the level of uncertainty. So we put when we believe we put the cellular phone here, okay, that was a discussion we did, okay? So when I put my cellular phone here, by the way, we put the cellular phone nominally at the center of the point, right? So that means that I have a cellular phone number 1, which is put in the center, cellular phone number 2. Now, but you know, we don't know where is the accelerometer, okay? So when I put the phone one, the accelerometer is here, and the other is the accelerometer there. Then I put another phone, another accelerometer there, another accelerometer, another accelerometer. You see, in my experiment, I have the position of the MEMS, which is varying within the nominal position. So it's a kind of saying that, if I want to represent where is the position of the accelerometer, I am better to say that the position of the accelerometer is nominally there, plus a random term, which is representative of my uncertainty about what is the true position of the MEMS, of the accelerometer inside the phone. I don't know where is it. I mean, I can open it, okay? I can open, I can see, I can go to the forum, they can tell me where it is. But there's another point. I mean, about the accelerometer, when this one is vibrate home. So about vibration, if I have a wave, when I have a phone, we discussed last year, but so let me make here a comment about that. Okay, when I have a wave that is propagating, okay, so imagine that this is the table, okay, just to represent, and I put a cellular phone here, and the accelerometer is here. This is accelerometer. Okay, this is the phone, and and there is a wave that is propagating. Imagine it's a hit, boom. Okay, so I have I have a hit which is propagating here. Now, when the hit is, I'm exaggerating, when the hit is here, what's happened is that this one is tilting up, and the other is tilting down. Okay, so when it's passing through, this one is not a point measurement. So the effect of the phone is to low pass filter, especially the data. So that is an additional element which makes the experiment uncertain and so on. So since the very stupid experiment like this has a lot of uncertainty, the most convenient way is to model all these uncertainties by stochastic parameters. So this is the reason why, we are studying the statistical part. The statistical part is motivated by the fact that our experiment is very limited, okay? And even studying the stocks value of Apple, because we want to become rich, the data set is virtually unlimited. But every phenomenon happens in 1, 2, 3 days. So that means that your estimator is 3 days longer. So it's not a big data in that case. If you want to establish what is the behavior of the stocks in the market, your data is not a big data. It's limited because it's few days. If you make the prediction in long term, that's fine, but it's useless. So I never look at the prediction on the long term. Okay, so I look at the prediction in the short term. And my prediction in the short term is not a big. So anyway, so let's move forward. So my model, okay, is not this one, but I prefer to represent my data as provided by some model, which might contain statistical part, stochastic part or not, and some noise. Okay? In big data, noise, is something that does not exist. It's something that is not classifiable in a specific way. Now, what does the estimation theory? The estimation theory is to infer the value of a limited number of p parameters. Okay, so which means p is a small set, p parameters. Okay, from a judicious analysis of order set xn. So which means I take an order set, some data, and I want to get data. Okay. The estimator is any transformation on these n set. So my n set, my n samples, I indicate with x subscript n. Okay. So the estimator is any function of that xi. Okay? This is the estimator. So if I want to find the estimator, you know, about the stocks values, we did it. It's a linear, you know, we did the linear one. And I told you I can do even better, but you know, it's a linear one. So that one is a linear estimator. So what do we establish all together in the beginning, the first day or second day, was a linear estimator. Now we can give a name. So that linear aggressor is a linear estimator because we are trying to linearly estimate by combining linearly the data. Remember, linearly is similar as this. Here, this is linearly, okay? So linearly means that, you know, I'm linearly combining the data to get, for instance, the parameter. Now I call y, but you know, I mean, I can revise everything and call theta. So, I mean, linear estimator is a linear transformation. So a linear estimation, we say. We will see many times, you know, just to give you. The linear estimator, that means that theta is equal to a certain transformation of data plus the b. So the estimator is to get A to get B. These are the estimators. Okay? And this is the estimated value. Now, since theta depends on x, x is some way random, because I mean, it contains some random component, theta is a random. So any estimated value is a random. And the estimator is the function. Okay? So if you don't like estimator, substitute with the word function. So what is what is theta? Theta hat, the estimated value, is a function of the data. Okay? Now, this function is estimator. Okay? So, you know, we need to define, okay, if an estimator is good or bad. Now, there are, I mean, this is just for culture, okay? There are two ways of looking at the experiment. The so-called non-Bayesian and Bayesian approach. What is the non-Bayesian? The non-Bayesian is called the frequentist, okay? Non-Bayesian means I want to represent any measurement as a random variable, okay? So this is the non-Bayesian approach. Non-Bayesian say, okay, if I have x, this is data, I can represent any data as dependent, so as a parametric description of the probability density function. So which means I can describe this data by the probability density function of x that, you know, depends, let me write this way, and depends on t. This is the dependency of the parametric probability density function. So it's the dependency. Now this one is the so-called frequentist approach, which means the frequentist says that every experiment can be repeated. Okay? Up to some uncertainty, but you know, it can be repeated. Which means theta remains fixed. Theta is the same. Okay? So every experiment can be done in such a way that theta is fixed and can be repeated. So I can repeat the same experiment. Okay? So, you know, I want to do the second experiment. Okay, theta is fixed. I do the third, theta is fixed. So let's make an example. I have a sinusoid in time. Okay? I take the window. Well, the frequency is that, the amplitude is that, phase is that. Time, window. Okay, frequency is the same. I can repeat the experiment, but it's enough that I cut it, right? every cut is a, is a new experiment, but the parameters are fixed. Okay? It's not true. Are they always that? Now, I cut a sinusoid. Okay, when I cut a sinusoid, the amplitude is the same. Yeah. Frequency. Yeah. Phase. Phase is not the same. Because every time I cut it, the phase indicates what is the position of the origin with respect to the frequency of the sinusoid. So the phase is not deterministic. It's not repeatable. It's random, actually. Okay? But anyway, so I choose this kind of example for a reason. Now, okay, so but this is the frequentist approach, and the method that they are using is the so-called Laplacian function. And when I maximize this Laplacian is the maximum Laplacian method. We will discuss on that. The Bayesian approach says that the parameters are random, and by chance a deterministic parameter is just a random parameter which is fixed to a specific value. Now in that case, my goal is to get the probability density function of theta given that I measure of 1. So that means that for the Bayesian approach, the experiment is just one value. So, and when I make a new experiment, it's totally different. And I need to start all over again. So these are two different, approaches. I mean, the most common one, let me say just an historical reason. So the frequentist or non-Bayesian approach, it was very common till the half of the century of the last century, okay, so 1950 or so. Okay. Then since it was found that some very convenient way to make the update and computation, so it's only a matter of computing, so the computer, to make it this formula feasible, then we start using the Bayesian approach. And one of the Bayesian, is the bias filter, Kalman filter, and so on. Okay. Now, just before I want to stress again the fact that the Bayesian approach, the estimator is a function. Okay. So since an estimator is a function, so that means that is a transformation on these specific set of values. Okay. Now we said that we're now on a frequentist approach, which means the parameter is fixed. So every time I make an experiment, okay, so theta is the true theta is theta 0. Okay, so assuming that the theta 0, the theta 0 is a true one. So every time I make an experiment, I make an estimate. Every time I make an estimate, I get this theta hat. So I can repeat these experiments many times and estimate theta many times. So I use theta hat, which is a function. And so what I get is that, I get the histogram, if you like, which is like this one, okay? This is a histogram. This is the histogram of the estimated value of theta for varying the random component. So what we notice is that, we can describe the distribution, the probability of theta hat, given that theta 0. So this is the true one. Okay. Forget about the notation. So what I notice is that my estimator, is spread out. And this is the true value. So what I wish is that my estimator is behaving like this. You see? It's not dispersing, okay? So every time I make an estimate, it's always there. So, I need to define a metric. And the metric is, how good, how bad is the estimate. Now, if an estimator, you know, is behaving this way, imagine this is the true one. I have two estimators, huh? I make a scala, okay? And this is the true theta. This is the true one. Huh? Then, you know, I want to compare two estimators. One is, I don't know, it's broad, this one, okay? And the other is narrow here. This is the probability or the histogram of theta hat for the estimator 1 and the estimator 2. So these are two different estimators, these two different transformations. Let me call theta hat and theta tilde, because so that, you know, it's different, okay? I mean, the estimator, you know, theta hat is, you know, it's very funny. So theta hat is by cosine and multiplied by tangent, by hyperbolic, by blah, blah, blah. It's very complicated, okay? And then I have a second one. Theta tilde is another estimate which is linear, okay? So we have two different estimators. I mean, it's any function. So I can give you a problem. Blah, 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 blah. Given this problem, I give you the data. And if I don't give you anything else, everybody of you comes with an idea of estimator. So one can be linear, the other can be non-linear, the other can be tangent, the other can be likes a trigonometric function, the other likes the logarithmic, the other likes whatever, comes a different function. Okay? So given the estimator, so you know, given different estimator, I need to establish which one is better. Okay? So, because I mean, I can accept any possible estimator. Remember, I can accept any possible estimator. Okay? But you know, what is important is how accurate is the estimation. And so, you know, the accuracy can be said in this way. For instance, I mean, the mean value of the estimator here coincides with the true value. Interesting. But you know, the values are quite dispersed. Okay? So since the mean value of the estimator theta hat, depending on n samples, coincide with theta 0, then you know that means that it's a property that we like it. Now this property is called bias. Now, and if the mean coincides with the true value, the estimator is unbiased. Okay. Now, what about this one? Yeah, if I compute the mean, you know, the mean is here. So the expectation of theta tilde n is different from theta 0. Okay, so this estimator is biased. Bias is, you know, means that the mean does not coincide with the true one. So which means, you know, that if I repeat the experiments many times, I compute the mean is not coincident with the true one. Usually when there is a bias, this means that the estimator contains some part which is wrong. So if it is biased, that means that this part can be shifted there. This means that it contains some, you know, distortion in the data. So you are using the data in a wrong way. Okay? I mean, stupidly, I can take the new theta tilde and correct it for this. And the estimator will be unbiased. Okay. Now, what about, you know, about these two estimators? What about the dispersion? Well, the dispersion, this one is very dispersed. So this one has a good property, which is, you know, the mean value stays there. So in other words, when I calculate the mean, the value, you know, it fluctuates around the truth. Okay? On the other hand, this one, this is the true mean and this fluctuates much less. Okay? The second case. So the dispersion of the second is much lower than the first. Okay? Good. Now, it depends. In some cases, this will be better than the other, and this can be better than the other. It depends. Okay. Now, another property. What's happened if n is going to infinity? What does it mean? It means that what's happened if I increase the number of samples? If I buy more data? If I make my experiment with the phone and I put an additional phone, 2 phone, 3 phone more, okay? So my goal is to understand, to see if I spend more, I gain more. Now, it might happen that if n is going to infinite, this one shrinks more, gets narrow. You see? Okay, perfect. So this estimator, is in some way is made in such a way that the more I use the data, and the better I go. It's less and less dispersed. Okay? This is consistent. The estimator is consistent, which means, the more I spend, the better I go. Perhaps, the second estimator does nothing. Okay? It doesn't change. So the second estimator is biased, and the more I spend, I don't gain anything. It's already inaccurate, and it remains inaccurate, whatever I do with my new data. Okay? So the first one is a good estimator, even if apparently it seems bad because it has a lot of erratic values when I estimate that. But when I spend more, it goes better. Now I put you in a bad position. What about if the second estimator is going to there when n is going to infinity? So when n is going to infinity, the second estimator has a dispersion that is limited, but goes to have a mean which is coincident with the other. Well, now that means that in this case the estimator is biased, but it is asymptotically unbiased. Okay, all these properties, will set the basis for the discussion about the estimators that we continue Friday and tomorrow we will exercise. Okay.